Hello students, welcome to Educate. We are going to study first chapter of physics, class 12. So, you know basic type of charges like positive and negative charges, and you also know that like charges repel each other. Suppose there is positive charge here and there is positive charge here, then they will repel each other, whereas opposite charges will attract each other. Suppose this is negative, this is positive, then there will be force of attraction. And similarly, if both are negative, in that case also there will be repulsion. So generally repulsive force should be written like this. Suppose these are positive charges, so here arrow should be outward, and if one is negative another is positive, then arrow should be inward like this. So here this should have been like this, not this, but it's okay. And here forces are like this will be attracted by this charge, and this will be attracted by this charge. Here both will move apart, here both will come closer. In this case also both will move apart. So now here we are going to study the quantization of charge. So you know conductors and insulators, they are very basic things, so I'm not going to explain. Charge is conserved. So charge is conserved means total charge on an isolated body remains same. Suppose a neutron converts into proton and electron. Suppose you are given a neutron and it converts into proton and electron. So in that case also, what happens? Total positive charge on this and total negative charge on this will be same as charge on this. Here charge is 0, and you know charge on proton will be plus 1.6 into 10 to the power minus 19 coulomb, and that on electron is minus 1.6 into 10 to the power minus 19 coulomb. So here total charge is 0. So we can say that for an isolated system, total charge remains conserved. The same thing is given here. If you read it, total charge of an isolated system is always conserved. Now, let's see further that what is quantization of charge. So you know charge on any object Q is plus minus Ne, where N is number of electrons and E is electronic charge, and you remember E equal to 1.6 into 10 to the power minus 19 coulomb in magnitude. Although there is negative sign, I have not written it. So it can't be in fraction, that if you say that a body contains 3.5 electrons, so that is not possible. 4.2 electrons, that is not possible. So quantization charge means it will be integral multiple of electronic charge, and this fact was established by Millikan in 1912. Now, if you want to find out total charge on a body and you are given number of electrons and number of protons, then easily you can calculate. We will do certain numericals based on this concept, so thing will become very clear. Now, here there is one question. If you can see example number 1, if 10 power 9 electrons move out of a body to another body every second, how much time is required to get a total charge of 1 coulomb on the other body? So here let's make calculation from formula Q equal to Ne. Here total charge required is 1 coulomb. So 1 coulomb, take it 1, then N is to be found. Electronic charge is 1.6 into 10 to the power minus 19. So n will be equal to 1 divided by 1.6 into 10 to the power minus 19. So you can make it 10 upon 16 and then make it 10 power 19. One more 10 you can take from here, so this will become 100 into 10 to the power 18 divided by 16. If you simplify, you will get 6.25 into 10 to the power 18 electrons. So this much number of electrons are needed, and in our question 10 power 9 electrons are transferred. 10 power 9 electrons are transferred in 1 second, electrons per second. So total time is required. So this is simple unitary rule. So you can say time equal to total number of electrons divided by a rate of transfer of electrons. So total number of electrons are given here. So total number of electrons, so times, so T equal to total number of electrons are 6.25 into 10 to the power 18 divided by 10 power 9. Now simplify 6.25 into 10 to the power 9 seconds. Now you can convert it into minutes, then hour, then days, then years, etc. So if you evaluate it, it will be around 198 years. So that is too much time. Now there is another question. The question says, how much positive and negative charge is there in a cup of water? This is also a good question. So we can imagine that 1 cup of water is equivalent to 250 gram. So here mass is given 250 gram. Now we have to find out number of moles. So number of moles given mass divided by molecular mass. Since we are talking about water, so water means H2O. So what is molecular mass here? 2 into 1 plus 16, that is 18. So divided 250 divided by 18 moles. And if you remember, 1 mole contains Na means Avogadro number, La number of molecules. So total molecules, total water molecules equal to number of moles 250 by 18 multiplied by Avogadro number. So Avogadro 6.022 into 10 to the power 23. Now further, our purpose is to find out number of electrons or protons. So let's consider electrons because they are equal, because it will be neutral. So in 1 molecule of water, how many electrons are there? H2O means HO. 1 electron here, and then 8 electrons here. So total 10 electrons. So number of electrons, you can say number of electrons will be 10 times this value. 250 divided by 18 times 6.022 into 10 to the power 23. So you can evaluate it and you can get the answer. If you wish to convert this electronic charge into Coulomb, so number of electrons you will find, and after that you can write total charge. So total charge will be how much? So charge, you can write Q equal to Ne. You have got number of electrons by calculating like this as I told you, and then multiply N into 1.6 into 10 power minus 19. Then your answer will come out to be around 1.34 into 10 to the power 7 coulomb. So I think you have understood. Question is simple. Now we are going to study Coulomb's law. What is Coulomb's law? So Coulomb's law is applied to find the force between two charges, whether they are like or unlike. So only nature will change, but strength of force will remain same. So let's write the law, and based on that law we will do some calculations. So if one charge is here Q1, another charge is here Q2, and suppose separation is R, in that case force between the two charges will be F equal to 1 upon 4 pi epsilon naught Q1 into Q2 divided by R square. Now you can write either Q1, Q2 in capital, that does not matter. Here, what is this 1 upon 4 pi epsilon naught? So 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power 9, then Newton meter square divided by Coulomb square. Now there is one question in your mind, why 1 upon 4 pi epsilon naught has this unit? So we can evaluate easily. Here we have F equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Our concern is to find this quantity, so keep it as it is 1 pi 4 pi epsilon naught, 1 upon 4 pi epsilon naught, and then shift this to this side, F R square divided by Q1 into Q2. Now put the units. F is in Newton, R square will be in meter square, divided by charge will be Coulomb square. So we have got the unit. And you can also find the value of epsilon naught. You can shift this epsilon naught to this side, and then 9 into 10 power 9 in denominator, then simplify 8.85 into 10 power minus 12. You will get that value also. Now here one important point is given. While the Coulomb's law, a simple mathematical statement, was initially experimentally arrived in the manner described above, here certain thing is given that I am not going to explain. Then here range is given up to subatomic level around 10 power minus 10 meter. So this tells the validity, means even in subatomic level Coulomb's law is valid. If distance is large, it is still valid. So sometimes the question comes that what is the range of Coulomb's law? So you can say that starting from subatomic level, it is valid till any level. Now we have seen how to evaluate. Now let's do some questions, and suppose we take two charges. One charge is here, say this is positive. So let's understand by some example. Suppose this is plus 2 microcoulomb here, and here minus 3 microcoulomb, and say separation is 2 meters. Now what will happen? This charge will exert positive force on this charge, so it will try to move in this direction. Or if you take it stationary, then this charge will move in this direction. So direction we will indicate like this. So force on this charge, suppose you want to evaluate, so you can say it will be 9 into 10 to the power 9 into product of two charges, so 2 into 3 into, it is in microcoulomb, micro means 10 power minus 6, 2 times, so 10 power minus 12 divided by separation square, 2 square Newton. So you have understood. Now suppose the two charges are of same nature. So suppose this is 2 microcoulomb, this is 2 microcoulomb, so force will be in this direction. So this will be repulsive force. Calculation is same. By same method you can calculate. Suppose this is 2 meter, then again you can value A. But when you are writing the arrows, then in that case you will you will see that arrows are directed away from each other. So this gives the origin of vector form of Coulomb's law, where we put and like we write F21 equal to minus F12, and that also establishes the fact that to every action there is equal and opposite reaction. So we will study those things in detail later on. Now here the same thing is written like F21. There are objects named as 1 and 2 having charges Q1 and Q2. Then force on first object. Here force on second object due to first will be 1 upon 4 pi epsilon naught Q1 Q2 divided by R21 square. R21 is a separation, and then unit vector R21. Similarly, if you change the script like F12 you keep here, then in that case this distance will be R12 square, although square R12 square R21 square. It's same thing here, only vector, unit vector will change its direction. So you will write here R12 cap, and no other changes are there. But you must notice that R21 vector, unit vector R21 must be opposite of R12. Now we are going to see the next thing. Here there is one question. Example number 3, NCERT textbook. So Coulomb's law for electrostatic force between 2 point charges and Newton's law for gravitational force between 2 stationary point masses both have inverse square dependence on the distance between the charges and masses respectively. Compare the strength of these forces by determining the ratio of their magnitudes for an electron and a proton. For 2 protons, estimate the acceleration of electron and proton due to the electrical force of their mutual attraction when they are 1 angstrom away, and certain information is given. So if you remember, to get the force you can apply F equal to 9 into 10 to the power 9 times Q1 Q2. Here, since you have to find out the force between electron and proton, so they will have same charges. So in negative sign is used, it means forces of attractive nature. So this is general notation. So attractive force is given negative sign, and 9 into 10 power 9, this value 1 upon 4 pi epsilon naught times E square. E square means electronic charge square. So 1.6 into 10 to the power minus 19. You can square it. Divided by separation is given 1 angstrom. So 10 power minus 10 whole square, and you can evaluate it. This is one case. And if you want to make comparison, in that case between this, suppose this is electrostatic force, we write Fe, and suppose gravitational force we want to find out, so let's denote it as Fg. What is the formula for gravitational force? Do you remember? F equal to G times m1 m2 divided by R square. So you can put the values 6.67 into 10 to the power minus 11 into masses. Mass of proton and mass of electrons are given. Sorry. So it is 1.67 into 10 to the power minus 27 multiplied by 9.11 into 10 to the power minus 31 divided by separation is same, 10 power minus 10 whole square. Now if you put the ratios of the two, if you write Fe, electrostatic force, divided by gravitational force, what do you observe? This denominator term will vanish, only numerators will be left, but the value will be very large as compared to this one. Means the electrostatic force will be very large as compared to the gravitational force, and it will be around 2.4 into 10 power 39. In exams, sometimes such question comes. Find the unit or dimension of, suppose it is given the quantity like K times Q1 Q2 divided by GM1 M2. Or if these are charges in terms of electronic charge, suppose this is E, so we can write it Ke square divided by G times mass of proton into mass of electron. And suppose you want to find out what is the unit or what is the dimension of this thing. So if you observe carefully, in the formula F electrostatic 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Here this term can be written as K. So K times Q1 Q2 divided by R square, and F gravitational is equal to G times M proton M electron. Here we are taking charge on electron, charge on proton. So E square we can write here K times E square divided by R square, and here G MP ME divided by R square. If we divide the two, force upon force, we are just doing FE upon FP, means force upon force. So it will be dimensionless. It will have no unit. Although values will be like this, K E square divided by R square will cancel out. G times MP into ME. So you can easily tell. Here in our question, we have found the ratio of the two forces as you have seen, and that comes out to be 2.4 into 10 power 9. This is Fe upon Fg in case of this is mass of proton, mass of electron, discharge. On similar line, the ratio of magnitude of electric force to the gravitational force between two protons. In previous case, we have considered a proton and an electron. The same thing we can do in terms of two protons. Then ratio will be little smaller. This time this will be 1.3 into 10 power 26, and that is over. I think you can easily calculate. Now, here same thing is explained that this quantity Fe upon Fg is dimensionless, as we have already discussed. Now, let's see next situation. Here, in this picture, what is happening? Here, situation is shown. A charged metallic sphere A is suspended by a nylon thread. Another charged metallic sphere B held by an insulating. Let's read the question fully, and after that I will tell you the solution. So handle is brought close to A such that distance between their centers is 10 centimeter as shown in the figure. The resulting repulsion of A is noted, and then sphere A and B are touched by uncharged sphere C and D respectively as shown in the figure. C and D are then removed and B is brought closer to A at distance pi centimeter they are kept. So situation, whatever they have discussed here, let's summarize it, then thing will become clearer for you. So here we imagine the situation that suppose this is a body having charge Q1, let's take its value say 5 microcoulomb. There is another body here, so this is body A, this is body B. Suppose it has charge Q2. Q2 say it is -3 microcoulomb, and the separation between their centers is suppose 1 meter for ease of calculation, I have taken 1 meter. If we find the force between these two charges, so what will it be? Will it be attractive or repulsive? This is positive, this is negative. So there will be attractive force. So 9 into 10 to the power 9 into Q1, Q2, that is 5 into 3 into 10 to the power minus 12 divided by 1 square Newton. So this is the force that exists between these two charged bodies. Now, if we reduce the distance, then what will happen? Suppose we make this distance to half. So will force change? Let's denote this as F1. Now, new situation, suppose this point A. New situation when separation is decreased to 1 by 2 meter. Means they are brought closer. So, by what factor the force will increase? Let's see. So, in this case, F2 equal to 9 into 10 to the power 9 into 5 into 3 into 10 power minus 12, and then this will become 1 by 2 square. So 1 and here 4. So what are you observing? When distance is halved, force is 4 times. Suppose distance is made 1/3. Next case we see F3 equal to, then what will happen? 9 into 10 to the power 9 into 5 into 3 into 10 to the power minus 12 divided by 1 upon 3 square. So it will become 9 times. Correct? Because force, if you analyze, so force depends on products of charges Q1 and Q2, and force is inversely proportional to square of distance between them. So definitely in the order of square it is increasing when you are bringing closer. If you take them apart, then force will decrease. Like if you double the distance, force will become 1/4. If you triple the distance, then force will become 1 by 9 times. So this is the case when distance between the two charges is varied. Now another situation will be there, that suppose we have previous situation we are discussing. Suppose this is body A, this is body B. Suppose this is say 4 or 5 microcoulomb, this is minus 3 microcoulomb, and separation is 1 meter. Is okay. Here in this case we can find the force 9 into 10 to the power 9 into 5 into 3 into 10 to the power minus 12 divided by 1 Newton, as we have already discussed. Now suppose there is a third body, body C, which has Q equal to 0, means there is no charge. Now we bring this body closer to this body and touch with body A. Then what happens? When this body C comes in contact with body A, then charge on A will be equally shared between A and C. Now situation is like this. A will have charge 5 by 2 microcoulomb. Now C will have charge 5 by 2 microcoulomb. Both will have equal charges. And then body C goes near to B and the two touch each other. So now what happens? B is having charge minus 3 microcoulomb and C is having charge plus 5 by 2 microcoulomb. Now the two charges will be shared equally. So you can, first of all, let's find total charge. So minus 6 plus 5 divided by 2, that is minus 1 by 2 coulomb charge is total charge left when the two body touches. But the concept is that the two bodies will share the charges equally. Now this minus 1 by 2 microcoulomb charge will be shared by the two bodies. So each will have minus 1 by 4 microcoulomb. This will also have minus 1 by 4 microcoulomb. Now again the two bodies are placed at their original places, like B will be here with charge minus 1 by 4 microcoulomb. And third body, which has also got final charge minus 1 by 4 microcoulomb, is removed from the scene. Now this is new situation and separation is again 1 meter. You have to find out what is the force between the two. So you can find F new. So what will it be? In that case, again 9 into 10 to the power 9 into this will be 5 by 2. This will be 1 by 4. Sign we will not write. Again it is attractive, no doubt. 1 by 4 into 10 to the power minus 12 being in microcoulomb divided by 1 square. Now we can make comparison. What change has taken place between in the forces in between these two cases when the C body C was away and when body C touches A and B in order and removed. So we have understood the concept. The same thing is discussed here in this example. If you read it carefully, you will find that body A was having some charge, body B was having another charge. When they share and then when charge is shared and they are removed. Another situation we can discuss in similar way. Like suppose this is body A, this is body B, and suppose it has no charge. Suppose this has 0 charge, here Q equal to 0 and it has charge Q. And the separation is suppose R, in that case force between them will be 0. But now if this body comes in contact with this body, then charge will be equally shared. Both bodies will have charge Q by 2, Q by 2. And then again if they are kept at the same separation, in that case what will be the force? So in that case force will be 1 upon 4 pi epsilon naught, then Q by 2 into Q by 2 divided by separation square. So this will be 1 by 4 times 1 upon 4 pi epsilon naught times Q1 Q2 divided by R square or Q square divided by R square. So such type of situation is shown here in this question. Let's read the question. Let's find out if there is something else. So we will discuss. Here let the original charge on sphere A be Q and that on B be Q dash. So two bodies are having different charges, right? Now what happens? At a distance R between their centers, the magnitude of the force on each is given by, as we have discussed, here situations like this. This is body A, this is body B. It is having charge Q, it is having charge Q dash, and separation is say R. In that case, F will be equal to, let's write here K, 1 upon 4 pi epsilon naught equal to, later on, or we can write 1 upon 4 pi epsilon naught, and then we write Q times Q dash divided by R square. Now, suppose we make the two bodies touch each other, then what will happen? Or if there is something else, let's see what is happening. Neglecting the size of spheres A and B in comparison to R. When an identical but uncharged sphere C touches A, the charge distributes on A and C by symmetry. As I told you, if any uncharged body touches the charged body, then charge will be equally shared. Then each sphere carries a charge Q by 2. Similarly, after D touches B, here situation is different. The distribution of charge is Q by dash. Then, so here situation is quite good that this is body. Once again, I will tell you. So here, this is body A, this is body B. So it has charge suppose Q and it has charge suppose Q dash. Now, a body C uncharged, Q equal to 0, comes in contact with body A. So what will happen? Charge will be equally shared. So now situation of A will be like this. Means A will be left with charge Q by 2. Now there is another body, this is body C, there is another body without charge and that comes in contact with body B having charge Q dash. So again same thing will happen. The charge on B will be equally shared between B and D. So new situation of B, when D is removed, B will have charge Q dash by 2. And now if we find the force, suppose we say it F nu, then it will be equal to 1 upon 4 pi epsilon naught, and then Q by 2 into Q dash by 2 into R square. So this is the case that they have discussed. One more thing. In place of R, suppose earlier the separation was R and now suppose it is made R by 2. Then what will happen? Here if we write R by 2, then it will get squared. So R square by 4, then these two terms will get cancelled and we will get same force. I think you have understood. This question is quite good and you can do it. Now, here forces between multiple charges. Before going through this concept, I am going to give you one example whereby you will better understand this concept. So let's see the case. Suppose here there is one charge Q0, here there is another charge Q1, there is third charge Q2, then Q3, then Q4. There are 4 charges and separation is given. This is R1, up to here this is R2, up to here this is R3, and up to here this is R4. Suppose you have to find out the net force on Q0 due to these charges. So it is very simple. F Q0 can be written as F Q0 and 1. Q0 1 means force between these two, plus F Q02 plus F Q03 plus F Q04. So 1 upon 4 pi epsilon naught 0 will be present in every term. So I am writing it outside. Then Q0 Q1 divided by R1 square. First distance is R1 square plus even Q0 can be taken out, but I am writing it Q0 Q2 divided by R2 square plus Q0 Q3 divided by R3 square plus Q0 Q4 divided by R4 square. So we can take out Q0 upon 4 pi epsilon naught, and then we can write Q1 upon R1 square plus Q2 upon R2 square plus Q3 upon R3 square plus Q4 upon R4 square. And this is how we can evaluate. So what do we conclude? Presence of another charge does not interfere, means does not disturb the force between any two charges. If you are evaluating force between Q0 and Q4, so you have to ignore the presence of these 3 charges. If you are calculating force between Q2 and Q0, forget other charges and evaluate separately, and then suppose you want to find out the total force on any particular charge, in that case you have to sum them up. The same thing is given here. Here forces between multiple charges. In the diagram, if you observe here, suppose we want to calculate force on this charge. So there are charge system here. I can show you in better way. Suppose here there is one charge, say this is Q1, here there is Q2, here there is another charge Q3, and there is another charge here Q4, and separations are given. Say this is R1, this is R2, this is R3. Now, one thing you have to note, that is the nature of charge. Here suppose Q2 is positive. We will do numericals on it, then you will understand it in better way, but it's okay. We are taking this positive, this negative, and this also negative. And now let's see what is the net force on charge Q2. So if angle will be given, we can easily evaluate. Here just I will show you the direction. Later on we will evaluate such type of questions with certain angles. So here what will happen? If you consider that this charge is fixed, then in which direction charge Q2 will move? There will be force of attraction between Q2 and Q3. So this charge will try to move in this direction. So this force will be in this direction. Here this is negative, this is positive. So here again, this charge will tend to move in this direction. Here this is positive, this is positive. Now, if you assume that this charge is fixed, then you can consider the motion of this charge. This is positive, this is positive. So this will try to move in this direction. So this force will be in this direction. Then we will evaluate the net force and then we can tell that in which direction with what force this charge will move. So we will do numericals based on it. So thing will be very clear. Now, let's see here, same concept as I told you is explained. Let's see this question. Consider three charges Q1, Q2, Q3 each equal to Q at vertices of an equilateral triangle of side L. What is the force on a charge Q with the same sign as Q placed at the centroid of the triangle? So let's see the situation. This is good question and we can easily understand it. So you are given, suppose this is equilateral triangle and here charge Q, here charge Q, here charge Q, and this side is say L, this side is L, this side is L. At the centroid there is charge Q, but in our question it is given that Q with the same sign. So suppose if we take small q positive, then capital Q will also be positive. So now consider the situation of these two. Suppose this distance is x. Later on we will do evaluation what is the value of x in terms of L, but here our concern is just to find out the force, as force will be 0, so why to calculate that thing. So let's see, this distance is x, here this distance is also x, this distance will also be x because this is position of centroid. Now, so and if you find these angles, you will see that theta in each case will be 120 degree. Now, let's see the force, but this is positive, this is positive. You have to find out the force on this. It means you will consider that this charge is fixed. Then what is the direction of motion of this charge? This is positive, this is positive. So it will tend to move in this direction. So F1 will be downward. Now, this is positive, and if you consider that this charge is fixed, then this charge will get repelled in this direction. So it will move in this direction. Now, the same is true here. This is positive. So if you consider that this charge is fixed, then this will move in this direction. So there are three forces, and this is F2, this is F3, and they all have same magnitude. So let's denote them as F, F, and F. Angle between any two forces is 120 degree, 120 degree, 120. If you remember, if three vectors are equal in magnitude and they are inclined to each other at 120 degree, then net result will be 0. So here net answer will be 0, but there is no question why this is 0. So let's see. Suppose this angle is 120 degree. Now this is F, this is F. We can find the resultant. So resultant can be found by using formula F square plus f square plus 2f cos 120 degree. So cos 120 degree is minus half. So this will give f square plus f square minus f square. So it will give f and its angle will be between the two. So you will get one force in this direction, another force in this direction. This is f, this is f. So hence the two forces will get cancelled and net result will be 0. So in this situation, in our question, here the situation is shown. Charge Q is at the centroid and these three charges are at the vertices of equilateral triangle. So net force on the charge capital Q must be 0. Here, if you wish, you can see in the solution also. So it is evaluated and the last result, it is clear also by symmetry that the three forces will sum to 0. So suppose that the resultant force was not 0 but in some direction, consider what would happen if the system was rotated through 60 degree. So that case we will consider later on. But you have understood that net force will be 0. We will see other questions in next lecture. Thank you. Team Educate.